Today, we will be completing our lecture series on quantum mechanics, quantum chemistry, and then we will start with molecular dynamics simulations. We will speak also about other simulation techniques a little bit. So what about basis sets? We were left here yesterday. We represent our electronic structure with a set of 1 electron orbitals. As you are familiar with by now, these are the Hartree-Fock and density functional theory relationships. One is with the wave function, the other one uses density, and they are related to orbitals, molecular orbitals, which are linear combinations. So molecular orbitals or Coskuner orbitals are really important for quantum chemistry. And when it comes to the linear combination of basis functions, we are familiar with it by now too. We represent molecular orbitals as linear combinations as basis functions. And here in this relationship, we have an artificial spin function, we have the coefficient in linear expansion, and we have the basis function with a fixed form. So what are the basic functions? Basis functions. Basis functions can take any mathematical form. But the forms we choose should, first of all, provide a good representation of the electron density. So, for example, electron density is large in core orbitals, bonds, lone pairs, etc. But it's small when you go far away from nuclei, right? And it should be enabling us to perform computations. So it shouldn't be too expensive or impossible to do the computations with the mathematical equations that we are having. So when it comes to atom-centric basis functions, most quantum chemical programs use basis functions that are centered on specific atoms. And here you have the STO and GTO representations with different basis sets here, STO3G, STO2G, STO1G. The wave function must exhibit a cusp. This is a cusp here at the nucleus, and the wave function must decay exponentially, as you can see here, right? Here, at large distances from nucleus. And these properties are satisfied by Slater functions, as you know. We have the normalization constant. We have the alpha controls. The alpha controls the rate of decay and the position of atom on which the function is centered. So Slater orbital functions, the advantages of it are they exhibit the cusp condition. So here you see that, the cusp. They capture correct exponential decay, but disadvantages are they are mathematically inconvenient. They cannot capture 3 or 4 center integrals analytically with Slater orbitals, and they have to employ costly numerical methods. When it comes to 3 and 4 center integrals, recall that in Hartree-Fock we have to evaluate orbitals involving 2 molecular orbitals. And at the end, when you start with 2 molecular orbitals, at the end you get a 4-centered integral. These cannot be evaluated analytically when you have a 4-centered integral if the basis functions are Slater orbitals. In practice, Slater orbitals are not used very often. Exceptions include ADF, which is a density functional theory code that uses Slater orbitals, and semi-empirical molecular orbital methods, which need 3 and 4 center integrals. When it comes to Gaussian-type basis function, Gaussian-type basis functions offer a convenient alternative to Slater-type functions, and here is the equation that you are familiar with by now. We had that yesterday too. Gaussians decay too quickly when you compare it here. They do not exhibit a cusp at the nucleus, but you can evaluate 3 and 4 center integrals analytically. Okay. And then we have contracted Gaussian functions. Can we take linear combinations of Gaussian basis functions to make them look more like Slater functions is the question. And the answer is yes, we can do that. And here is the expression to do that. We have an alpha D term and a C D term that needs to be C and alpha terms, coefficients that need to be optimized in this case, or fitted in this case. So when it comes to contracted Gaussian functions, the contracted Gaussian function is given by this equation. The degree of contraction is the CD part. And then we have the alpha D, which is the primitive exponent. The contraction coefficient is related to the degree of contraction. For each degree, you have to calculate it and sum it up. So this is the CD term. Each contracted Gaussian is one basis function. The contraction coefficients and primitive exponents are fixed in calculations. And this is the expression that we get at the end for the contracted Gaussian function. So the advantages of Gaussian orbitals is we can treat them mathematically. That's why they are used heavily. We can introduce nodal features. The disadvantages are we have to use a lot of basis functions to produce the behavior of Slater orbitals with the cusp and exponential decay. And the second disadvantage is that contraction coefficients and orbital exponents have to fit to either experimental data or other data, tedious work without a clear direction for improvement. The nodal behavior, when it comes to the nodal behavior, here you see the nodes. When you look at the wave function of 1s, 2s, and 3s orbitals, the radial components of atomic orbitals exhibits nodes. By setting some contraction coefficients to be negative, we can mimic monodal behavior with contracted Gaussians. And we use the same equation that we used before for this purpose. Then we have the angular behavior when it comes to basis sets. So atomic orbitals exhibit angular dependence in addition to radial dependence, right? We introduce angular behavior by multiplying Gaussian functions with angular functions. So you have to change the direction, right? X, Y, Z, or rotate it. So you need the angular behavior. And spherical harmonics is used usually. It's the most straightforward way to introduce the correct angular behavior in the mathematical form using spherical harmonics. And this is the equation. L is the angular momentum number, the azimuthal quantum number. It's 0 for S, as you are familiar with. It's 1 for P and 2 for D orbitals. M is the magnetic quantum number. It goes from minus L to plus L. This approach will give one S function, 3 P functions, 5 D functions, etc., for each Gaussian basis function. So we introduce, as we said before, the angular behavior by multiplying Gaussian functions with angular functions. And you can use Cartesian Gaussians. So spherical harmonics can be inconvenient to deal with. Instead, many codes use Cartesian Gaussians. So for d orbitals, for example, I would be 2, right? So we have that here. L would be 2. Here, in this case, we have xi, yi, and zi. And here, when you look at this, it would be 2, j would be 2, k would be 2, or I and j would be 1, or I and k would be 1, or j and k would be 1. Instead, many codes use Cartesian Gaussian functions. This gives 6 orbitals. 3 of them correspond to dxy, dxz, and dyz. Linear combinations give dz square and dx square minus y square. The 6th one has asymmetry. For f, g, and h orbitals, you get even more extra orbitals. Some programs can eliminate these, though. So Most programs can work with either spherical harmonics or Cartesian angular functions. In spherical harmonics cases, we use the minimum number of functions for each angular momentum, and it facilitates easy interpretation of results. That means it's easy to determine if S, P, or D electrons are contributing to a particular molecular orbital. When we use Cartesian angular functions, mathematically, it's very convenient. It uses, however, too many orbitals for higher angular momentum, and that means more computational effort. Different basis sets are designed to work with either spherical harmonics or Cartesian angular functions. So when it comes to contracted Gaussian functions, advantages of Gaussian orbitals is, as we said before, we can treat them mathematically, we can introduce nodal features. Disadvantages are we have to use a lot of basis functions to produce the behavior of Slater orbitals, and contraction coefficients and orbital exponents have to be fit to either experimental data or other data. Tedious work without a clear direction for improvement. And in general, we can state again that most quantum codes used for studying molecules use contracted Gaussian basis functions, and many different types of Gaussian basis sets have been developed for simulating molecules or biomolecules. So when it comes to basis sets, each contracted Gaussian function represents one basis function. A basis set is a set of basis functions that are centered on a specific atom. And basis sets usually include at least one basis function for each type of occupied orbital on the atom. So when I have, for example, the carbon atom, I have the electron configuration 1s2, 2s2, 2p2, right? So I have a contracted Gaussian for the 1s orbital. I have a contracted Gaussian for the 2s orbital. I have a contracted Gaussian for the 2p orbital. The 2p contracted Gaussian would be multiplied by a p angular function to give three different basis functions. That would be px, py, and pz, right? Note that three p functions are included even though there are only two p electrons on the carbon atom. So, basis sets in general, for hydrogen and helium, you need 1s functions, lithium to neon, 1s, 2s, and 2p functions, sodium to argon, 1s, 2s, 2p, 3s, and 3p functions. These are the minimum number of basis functions that must be included for each atom. And many basis sets include multiple orbitals for each atomic state and some higher angular momentum orbitals. And note that these are just mathematical functions. So one of the used basis sets is single zeta basis set. The single zeta basis set includes one contracted Gaussian basis function for each occupied type of orbital on the atom. These are also called minimal basis sets. STO-NG is an example to that. It's the most commonly used single zeta basis set. It contracts n primitive Gaussian functions. That's why it has the n in its name. The contraction coefficients and primitive exponents selected to give best fit to Slater type orbitals. And when you have three primitive Gaussian functions, STO and G becomes STO 3G, and it seems to provide the best balance of accuracy and cost. It's available for nearly all elements in the periodic table, but it's not suitable for quantitative calculations. It would be okay for qualitative studies, though. Then we have multiple zeta basis functions. Multiple zeta basis sets include multiple contracted Gaussian basis functions for each occupied type of orbital on the atom. And the number of Gaussians used to determine level of zeta, when you have two contracted Gaussians, it's called double zeta. When you have three contracted Gaussians, it's called triple zeta. The benefits are each contracted Gaussian function gets a variational coefficient in the definition of molecular orbitals, and more coefficients mean more variational flexibility to get a lower energy wave function, and we described that yesterday actually. More basis functions gives more flexibility in describing bonding. The disadvantage is that more basis functions and molecular orbital coefficients increase the computational cost and efforts. So CC, PV, and Z is an example. Basis functions still look to reproduce the results of calculations performed with highly correlated methods. We use n contracted Gaussian functions per atomic orbital. We can have CC-PV-DZ, CC-PV-TZ, etc. These basis sets are used for very accurate calculations, but high value of n leads to an impractical number of basis functions, meaning more computational cost, right? So split valence basis sets, these apply multiple zeta basis functions to valence states and single zeta basis functions to core states. Why do they do that? Because the core states are relatively independent of the biochemical environment, say, right? And do not require very much flexibility in their description. The valence states, on the other side, can participate in a wide range of bonding environments and meet the flexibility offered by multiple zeta basis functions. This approach strikes a balance between having a flexible description of the electronic structure and computational efficiency. So when it comes to split valence basis sets, yesterday we used in the example calculation the 631G basis set, right? This one is an example for applying multiple zeta basis functions to valence state and single zeta basis functions to core states, actually. 6 describes the core states, 3.1 describes valence states, and G means Gaussian basis set, okay? So, 321G is a double zeta split basis set. Each core state is treated with one contracted Gaussian composed of 3 primitive Gaussians. On the other side, 6311G is a triple zeta split valence basis set, so the computations are much more expensive with it. And the next topic that we can talk about is adding polarization into our functions. It is often necessary to include basis functions with higher angular momentum than the electrons in the atom. So here, for example, when you want to describe this SN2 reaction mechanism that has a trigonal bipyramidal state, the carbon atom is a transition state, you need orbitals of d symmetry, right? And p orbitals on hydrogen can account for differences in electron density along x and y direction when hydrogen is involved in bonds. These are the examples whereby you would need these. And in neither case do we suggest that d orbitals on carbon or p orbitals on hydrogen actually play a role in bonding, right? They don't play a role in bonding. But polarization functions just increase our mathematical flexibility when describing the electronic structure around a particular atom. So the polarization functions, it is often necessary to add them, and we add therefore P functions to hydrogen and helium, or D functions to lithium to neon and sodium to argon, and transition metals have F functions. They can also include even higher angular momenta, but usually less helpful and usually designated with double star or DP. So yesterday, when you looked at the basis sets, when you used games, you saw double star and DP. A star or a D means polarization functions are added to all atoms except hydrogen and helium. A double star or DP means polarization functions are added to all atoms, including hydrogen and helium. Usually, only one set of contracted Gaussians are added as polarization functions, regardless of level of zeta. The CC-PV And Z basis sets include polarization functions by construction. And then we have diffusion, right? Diffuse functions. Sometimes electrons are not localized close to atoms. So we use basis functions that decay very slowly with R. These are called diffuse functions. Diffuse functions, usually one set of diffuse functions is added to each occupied angular momentum in the atom. For example, hydrogen gets S diffuse functions, carbon gets S and P diffuse functions. These types of basis functions are needed for situations where electrons are not tightly bound to nuclei or where long-range interactions are relevant, such as anions, complexes, excited states. And they are designated with plus plus or AUG for augmented. 631 plus GDP basis set means that it includes diffuse functions on everything but hydrogen and helium. 631G plus plus GDP includes diffuse functions and polarization functions on all atoms, including hydrogen and helium. And AUG, augmented CCPVDZ, includes diffuse functions on all atoms. So which one should you use?
So the last one.
Yes.
Between 631 and our last AVTCC. Does both are peptide parameter?
So one is I can show you again. Here, this is CCPVNZ. This is a multiple zeta basis set. Okay. 631, on the other hand, is a split valence basis set, meaning you apply multiple zeta basis functions to valence states and single zeta basis functions to core states. These are different basis sets, how they are developed.
3 represent electron valence electron or something else. AU3. What it represents?
What do you mean?
Valence states. Does it represent the valency number or?
3 means one of the valence contracted Gaussian basis functions contains 3 primitive Gaussian functions. And 1 means the other valence contracted Gaussian basis function contains only 1 primitive Gaussian function.
What would be the number of electrons in this case?
It depends on what you are studying. I don't know. Depends on the element, depends on the molecule you are studying.
So we can apply the same for all atoms.
You can apply that to all atoms, yes. So which one should you use? You want to use the minimum number of basis functions to accurately describe your system. In general, the only way to find out the appropriate basis function is to do test calculations. And the literature can also provide guidance. But general guidelines are 3 to 1G can be a good starting point for preliminary qualitative calculations because it's fast. Polarization functions are always required for quantitatively. 631 GDP is a pretty good first guess at choosing a basis set. And going to 6311 GDP is often a waste of time. The CCPVNZ series of basis functions can be useful for highly accurate work. I like to use them in my research, particularly if you are using configuration interaction, coupled cluster, or SCF. Diffuse functions are necessary if describing long-range interactions, excited states, or anions. Otherwise, they are unnecessary and often pose numerical problems. Most basis sets were optimized to work with Hartree-Fock and ab initio methods, but they seem to work well with density functional theory as well. Most programs have a built-in library of basis sets, but if you don't find it, what you're looking for, You can get it from EMSL, PNL.gov, forms, basis form, HTML. You can visit that website right now, actually, to see the list of basis functions. Okay, have you opened the website? Yes. Games, you did that already, and now I will be talking about cost and accuracy. So, how can I get rid of this here? Oh, yeah. So, Orkun Hocam, this was one of your questions. Accuracy and cost. We have to strike a balance between computational accuracy and computational cost, usually. The number of basis functions, when you look at the degree of correlation captured approximately from Haji-Fogg to full CI, is a linear line, right? So it's increasing to get the exact wave function. So the number of basis functions, the degree of correlation that is captured, all are increasing. So when it comes to Haji-Fogg limitations, the result of a Haji-Fogg calculation with an infinite number of basis functions, it will never give the exact result, as you know by now. There will always be correlation energy missing in Haji-Fogg calculations, right? And can be extrapolated from a series of calculations. The Haji-Fogg limit will never reproduce exact results. Here you see the energy of the helium atom. The correlation energy never captured with Haji-Fogg, and improvement in variational energy from additional basis functions show that it's still, far away from the experimental. So just a second. Here we go. So there will always be correlation energy missing in Haji-Fogg and can be extrapolated from a series of calculations. When we compare it to full CI with an infinite basis set will provide the exact solution. Full CI calculations with finite basis sets are rarely feasible. Overall, this tells us that to systematically improve the accuracy of our calculations, we have to increase the basis set size and the amount of correlation captured by the simulation. So how costly are these methods actually? Generally, we look at how a method scales with the number of basis functions. The number of basis functions is related to the number of atoms in the system, right? Number of basis functions is also related to the quality of the basis set, right? And we saw the basis set just a few minutes ago. Hartree-Fock. The rate limiting step of a Hartree-Fock calculation is the evaluation of the two electron integrals. So as you can see here, it's really a rate limiting step here, and it involves a product of 4 different basis functions. We call it K4 scaling, can be reduced to K4 divided by 8 by symmetry, usually more than K3 in practice. When it comes to density functional theory, the rate limiting step of a DFT calculation is the evaluation of the two electron integrals, as you can see from these equations, and we had that yesterday. If we fit the density to a set of basis functions too, this costs also some time. And these are the auxiliary basis function, right? So it represents an improvement in scaling over Hartree-Fock, but although DFT scales better than Hartree-Fock, in practice, the two methods have similar computational costs. Then we have, when we look at correlated admission methods, similar analysis can be applied to other methods like MP2, Møller-Plesset, CISD, CZSDT, but we won't do it here, okay? Because I don't have the time to explain everything in this workshop. So here you have a table which I made that compares the accuracy and cost. So how costly are these methods? You can see that here. This gives an idea of how each method scales with the number of basis functions, and other factors determine the computational effort required per basis function. So when you have a full CI, you have a K factorial actually. It's a lot. So you can treat only a few atoms with full CI. So how does scaling affect calculations in practice? DFT and Hartree-Fock suitable for systems with up to a few hundred atoms. It can be used in geometry optimization, frequency calculations, and MP2 is suitable for systems with up to 50 atoms. It can be used in geometry optimization, frequency calculations. CCSDT is suitable for systems containing up to 20 atoms. And usually only single point energy calculations are conducted by it. And then using that result, you can do geometry optimization, for example. And full CI is suitable for systems containing only 3 to 4 atoms right now. Usually only single point calculations are conducted using full CI. So usually people are most interested in getting the geometry and energy, right? We talked about the potential energy surface, etc., yesterday. The geometry optimizations are usually only performed at the Hartree-Fock, DFT, or MP2 levels of theory because these are faster and can treat more number of atoms. Energies are calculated at various levels of theory. After you optimize the geometry, atomization energies are used as a test for reaction thermodynamics, and systematic studies of reaction barriers are less common. In general, you have to test out the methodology that you will use for your own case against experimental data or higher level quantum mechanical calculations. So the geometries are often relatively insensitive to the basis set. For a set of 20 small molecules, these are the results for Hartree-Fock 321G star and Hartree-Fock 631G star. There can be exceptions though. The geometries of molecular complexes often require diffuse functions, as we talked about it. And transition state structures can often be more sensitive to the basis set, and polarization functions are definitely required. So when you look at the geometries that were calculated with quantum chemical methods, geometries are often relatively insensitive to the theoretical method. And here you see Hartree-Fock and Algame methods underestimate bond lengths. We talked about that yesterday too, that they underestimate bond lengths. Here you see the results. GJ methods overestimate bond lengths. We talked about that yesterday too. Angles and dihedrons are usually good to within 2 to 3 degrees with all methods. And care must be taken for systems where dispersion effects, meaning van der Waals interactions, matter, since these effects are not treated correctly with Hartree-Fock or density functional theory. When it comes to energies, energies are very sensitive to methods and data sets. And DFT methods often provide best balance of cost and accuracy here. Hybrid DFT usually provides some improvement over pure DFT. And increasing basis set size does not always improve performance, as you can see here. So these results only represent a selected handful of reactions. In general, methods such as QCISDT and CCSDT are more accurate than DFT, density functional theory. Also, reporting averages hides the fact that some large individual errors exist. So please remark these. So when it comes to accuracy and cost, hybrid DFT methods are a good starting point if you are studying molecular systems without weak interactions or hydrogen bonds. For weakly bound systems, NP2 methods are an appropriate alternative. And Hartree-Fock has largely been replaced by DFT as the standard approach. Higher level methods may be needed for quantitative studies, okay? So you have to test your methodology, your method and your basis set against experimental data or a higher level of theory calculation. Strategies for optimizing the balance between cost and strategy when your system is simply too large for a DFT or NP2 calculation, or you require a level of quantitative accuracy that cannot be attained with DFT and NP2, you can truncate the system, apply different basis sets to different atoms, or use mixed level methods, or use more faster computers. So when you look at truncated systems, here is, for example, an example where MES is replaced with hydrogen here. It's a truncated system. Here the same. Here the same. Or you can use mixed level methods. That means geometries are relatively insensitive to the level of theory, as we said before. So why not do geometry optimization with lower level methods, right? You want to evaluate reaction energies and barriers for a 20 atom system at the CCSDT, CCPVTZ basis set level. Geometry optimizations involve numerous successive energy and force calculations. Just a single point energy calculation on a 20 atom system with CCSDT can take a very long time. So geometry optimization is generally not possible. So optimize with DFT, for example, using BGLYP with a smaller basis set like 631GD. And then using that optimized geometry, you can do the CCSDT, CCPVDZ calculation on the optimized structure, for example. So that's one of the ways that's done. And mixed level methods are presented by double slash. Here it separates the two methods. And here are more examples. Or computational considerations use parallel computing, right? And that changes the speed of the calculations with the number of processors. And these are the things that I wanted to say. And at the end, before I close the quantum mechanics topic, I would like to say that continuum solvation models are very important. And we did calculations yesterday with the water model, PCM. Solvation can have a significant effect on reaction energies, mechanisms, molecular structures, and molecular properties. When you do not add a solvent effect in your quantum calculations, it will be in the gas phase, right? So that's very unrealistic for biological systems. Ideally, we would like to consider explicit solvation of the solute. Explicit means you have the two hydrogen atoms and the oxygen atoms, and the hydrogen bonding is occurring in your system. But yesterday, we used only the dielectric medium of water, for example, in our calculations, right? And hydrogen bonding effects between water molecules were not included. Only one shell of solvent molecules will polarize the system too much then. So solvation can have a significant effect, as we said, and additional shells involve too many molecules, right? Your number of electrons is increasing. Individual configurations of solvent molecules are meaningless. We need to average over a large number of solvated systems. So accurate explicit solvation is not feasible with quantum mechanical or quantum chemical methods actually. So instead of explicit solvent molecules, we have a continuous medium with the dielectric constant of the solvent. Then we carve out a small void for the solute. The size and shape of the void depend on the size of the solvent and solute. It represents the region around the molecule that isn't accessible to the solute. Then we put the solute inside the cavity. So this is the solvation energy calculation. We have the energy of solvated molecule, the energy for cavity formation, and the energy in gas phase terms. So several equations for G exists too, like the Kirkwood-Osanger method. We have the dielectric constant, which is the epsilon here, dipole moment mu, and related to the size of cavity by A. So some of the models that are available are Kirkwood-Osanger. It's a very simple model, PCM and CPCM, which I forgot to write here is the Cosmo and Cosmo-RS models, which I like to use also in my calculations. And solvent effects are very useful when you look at zwitterionic systems, when you study the effect of solvent effects on reactions. And solution environment can change the geometry and energies of a molecule a lot, right? So this is it regarding quantum. Tomorrow we will be talking about quantum computing. Now, before I continue with molecular dynamics simulations, I would like to share a presentation that shows why molecular dynamics simulations are important. So, how many of you know what an intrinsically disordered protein is? What is it? What is an intrinsically disordered protein?
I am interested in molecular dynamics.
You have been using molecular dynamics?
Yeah.
What is an intrinsically disordered protein? It's my question. You don't. So, yes?
No. As the name suggests, it's intrinsically disordered, and it's where its function is coming from. It's not stable.
It doesn't have a stable three-dimensional structure, right?
Yes.
Yeah. But it has various functions usually. So it's against the structure-function relationship dilemma, right? In biology and medicine. So Today, I will be presenting a little bit of my studies about the universe of intrinsically disordered biopolymers using only molecular dynamics simulations, because the next topic is molecular dynamics. But we studied, and Jahid is here, he can tell more, or Iram or Melissa, we studied these systems using artificial intelligence too. And, right? And we published your papers. So, the only way to study these systems nowadays is not molecular dynamics. We will see tomorrow how to create and assemble using AI. But let's come back to molecular dynamics simulation, so intrinsically disordered biopolymers. The fathers of intrinsically disordered biopolymers are Pete Dunker and Vladimir Yuvarsky, very close friends and very good scientists. No words about that. So, what are intrinsically disordered proteins actually? Let's watch that.
Proteins are everywhere, in food, cosmetics, but most importantly in all living beings, in plants, animals, and of course humans. There they play an important role in growth, brain function, healing, and many other things. So what are proteins? Proteins are special molecules that are made from our genetic code as chains of amino acids that can fold up into three-dimensional structures. For the many processes in the living cell, there are thousands of different proteins with different shapes and sizes. Science has shown that the three-dimensional structure of the protein is important for its function, and the Protein Data Bank now contains a large number of protein structures. All these structures have helped us understand how proteins work. For example, it is now possible to create drugs that match the shape of proteins and so treat diseases. We call this a lock and key mechanism. Proteins also have flexible parts, for example to bind to other proteins. So-called hub proteins have many binding partners and change their shape depending on which partner they bind to. The importance of proteins' plasticity and flexibility is seen by the rapid increase in the number of reports about disorder in proteins. In fact, disorder has often been described in literature in many different terms, and one wonders why it took so long to realize that it is a research field in its own right. Only recently a single name was agreed on that shows how important it is: intrinsically disordered proteins, or IDPs. To illustrate flexibility in proteins, let's look at what happens when a protein unfolds. Where the folded form has a more or less fixed shape, the unfolded one looks like a flexible string that constantly changes shape. Such flexibility is very important. For example, in binding of two proteins where one has to adapt to the shape of the other. In diseases like Parkinson, Alzheimer and prion disease, healthy proteins unfold and refold into a different shape. For example, prion proteins normally contain helical structures that can change into a disease form with so-called beta sheets. These proteins then assemble into fibrillar aggregates, causing plaques to be formed in the brain. Disorder in proteins is so important that it is encoded in our genetic code, from which we can predict whether proteins are likely to become intrinsically disordered. So how do you study something that is always changing shape? IDPs pose big challenges, and many different techniques are used in this field of research.
So, IDPs at a glance, they like fixed three-dimensional ordered structures. They are disordered. Their discovery has disapproved structure-function paradigm in biology and medicine. because it states once you know the structure, you can predict the function of a protein, right? Well, it doesn't look like it. IDPs differ from structured proteins in many ways in their function, structure, sequence, interactions, evolution, and regulation. And their existence challenges Anfinsen's dogma, which got the Nobel Prize in chemistry in 1972. We showed that IDPs are common among disease-related proteins, including neurodegenerative diseases. So, when it comes to diseases, they are at the center of cardiovascular diseases, cancer, neurodegenerative diseases, type 2 diabetes, and prime diseases. And it makes them attractive drug targets. However, it's very, very difficult to produce a drug against these proteins that targets these proteins. Why is it very difficult? Because they are intrinsically disordered. They are always flexible, right? They are changing their shapes and conformations. And it's very, very difficult to predict their pockets, binding pockets. But we did that too. Thanks to Sinan, right? Using a machine learning algorithm along with physics-based studies. We will publish that paper soon too, hopefully. So in neurodegenerative diseases, for example, when you look at Alzheimer's and Parkinson's diseases, people have been investigating, scientists have been investigating that for decades, and there is no solution. And we hope that our methodology will help out to produce more useful and efficient drugs. So techniques and methods that are used are circular decoysm, UV, NMR, X-ray, mass spectrometry, small angle X-ray scattering, and computational techniques and methods. So now, regarding these techniques and methods, how do you define, how do you measure the structure of a protein? With which experimental technique would you measure the structure?
X-ray.
X-ray. And what else? NMR. Pyro-EM. Only the protein conformations. You're not interested in evidence yourself. Would you still use pyro? Jack, would you use pyro?
In some cases, yes, but for IT, so.
You would not. Why not?
Well, let's say if you these IPs, you can have a lot of different configurations, so it would be hard to assemble them with tree structure. But it's a well-thought thing to displace a couple of configurations, primarily on.
Yeah. So, IDPs, when it comes to IDP structure, it's difficult. In general, protein structures. Why is it? So is DNA. So, X-ray is a solid state. Is it a biological environment? So, X-ray structure, PDB data bank. I want you to go to protein data bank on Google and then click on the website. Is that possible on your laptops to go to protein data bank? How many of you are familiar with protein data bank? Can you type in Google protein data bank? And then go to that website. So when you look at the structures that are determined and exist in protein data bank, it's usually X-ray and then NMR, a little bit pyro-EM, right? Etc. So X-ray is in solid state. What is the problem with NMR, John?
Then get more time and get people.
Time is not the problem. Let's say we have the time. Scientifically, that's the limitation of NMR when it comes to
NMR is, as you can say, it's a magnetic sound. Not for.
Has nothing to do with it. It has size issues. In that measure like size, right? Okay. So you have size difference. Here we go. X-ray is not useful because it's a solid state. NMR, it's also useful for small size proteins, it is, but large size proteins, it isn't. Chi-OEM, it's very, very difficult to isolate and study conformational properties. So now we are to say that we are in the age of AI. On what does AI do? Training data. Where is that training data coming
From NMR.
NMR or X-ray, right? So you have solid state and small size things. So, but mostly you have solid state, right? Which has nothing to do with biology, right? So, and then we say we predict the structures of proteins in AI and all this. So what we do predict is the solid state structures of proteins. What would you need to do to come up with something that's evolutionary? What would you do, for example, to change this? What would you do? How would you?
Data and biological sources.
How are you going to measure that? There's no technique that can measure. That's not possible. So what else can you do? You can generate synthetic data. How are you going to generate it? How are you going to do that in solution phase? And how are you going to test it if it's accurate or not? It's not possible. So, how would you think we talked about continuum water models just 2 minutes ago? Right? With the dialect cut. So, what would you think when you integrate continuum implicit solvent models into AI? So you integrate physics-driven approaches with data-driven approaches, and then would that provide a solution to find the structure of the solution? Yes, it could, right? Not quantum solvent models, but there are also implicit solvent models that are used to class start then. So, okay, do you understand what the problems are nowadays? So computational techniques and methods are extremely useful, right? And these computational techniques and methods that we have in our group is bioinformatics, quantum mechanics, a little bit quantum computing, classical MD simulations, special sampling simulations, thermodynamics, and machine learning. Right? So today's topics are about Jochela type spinal muscular atrophy. This is have you ever heard about SMA disease? It's big in Turkey too. And this is the Jochela type of it. We will talk about that. And then we will talk about bio-inspired polymers for soft robotics using intrinsic disorders proteins. And then we will talk about AI-based structured prediction tools. And then I will start with molecular dynamics simulation so that after you see how important it is to have molecular dynamics. Okay, now it's time for a break, I guess.